In this segment, we'll start discussing the theorem of the maximum, which helps us to look at optimization problems in a very general way. And the proof of this result is quite involved, so we'll complete a portion of it and finish up in the next segment. We'll start by defining an optimization problem in a very general setting, and then we'll state the theorem of the maximum, which identifies conditions under which the solution to this optimization problem varies continuously with the underlying parameters of the problem. Now, the theorem of the maximum makes three claims. One, that the solution correspondence, which is the set of actions that results in a maximized value of the objective function, is compact valued. Two, that the solution correspondence is upper hemicontinuous. And three, that the optimized value of the objective function varies continuously with the parameters of the problem. And we'll prove the first two claims in this segment and leave the third for the next segment. So let's start by writing down an optimization problem in a very general way. So think of a parameter set, which we denote by capital theta. And this could be a set of preference parameters, technology parameters, endowments, or anything you like. But these parameters are not within the control of the decision maker. They're exogenous to the decision problem. And we'll be interested in the conditions under which the solution to the optimization problem varies continuously in these parameters. Next, consider a choice set, which we denote x. And this is the set of actions that could be feasible for some values of the parameters. Next, an objective function f, which we assume to be real valued, and this is what the decision maker is going to try to maximize. And the value of this objective function will depend both on the parameter and the choice made by the decision maker. Next, we define a constraint correspondence gamma, and this is the set of feasible actions at any given value of the parameter. So gamma identifies a subset of x that is feasible at any given parameter value theta. Next, we define a solution correspondence and denote this gamma star. And gamma star of theta represents the set of actions that result in a maximized value of the objective function, given the parameter value theta, and given that the choice is made from gamma of theta, which is the set of feasible actions at theta. And finally, the maximized value of the objective function is denoted f star of theta, and this is the best you can do if the parameter value turns out to be theta and you choose your action optimally from the set of feasible actions gamma of theta. And the key question that the theorem of the maximum tries to answer is whether the solution correspondence gamma star of theta and the maximized value of the objective function f star of theta are continuous, and in what sense. Remember that for correspondences we have multiple definitions of continuity, and it may be that the solution correspondence satisfies one but not the other of these. So now let's state the theorem. Let capital theta and x be two metric spaces, and recall that we're going to interpret theta as a parameter set and x as a set of actions. Let gamma be a compact valued correspondence with domain theta and codomain x, and this we'll interpret as the set of feasible actions at any given value of the parameter. And we're going to assume that gamma is compact valued. Now we define f as the objective function. This is real valued, and we're going to assume that it's continuous. And this tells us what the decision maker wants to optimize, and its value will depend both on the action taken and the parameter value. And we define f star of theta, so this is the maximized value of the objective function, and this is the highest value that the objective function can take, provided that an action x is chosen from the feasible set gamma of theta when the parameter value is theta. And we define gamma star of theta as the set of actions that result in this maximized value. In other words, gamma star of theta consists of the set of optimal actions, given that the parameter value is theta. And here's what the theorem states. It states that if gamma is continuous at a parameter value theta, then f star, which is the optimized value of the objective function, is continuous at theta, and gamma star, which is the solution correspondence, is compact valued and upper hemicontinuous at theta. Now note that the assumption that gamma is continuous at theta means that it is both upper hemicontinuous and lower hemicontinuous at theta, and we'll need to use both these facts. And what we'll do in the rest of the segment is prove the claim about gamma star, and we'll defer the proof of the claim about f star to the next segment. So first let's prove that gamma star of theta is compact at every theta. And to do this we need to recall some earlier results from the course. First, remember that any finite set in the set of real numbers is closed. Next, that for any continuous function, the inverse image of a closed set is closed. And third, recall that a closed subset of a compact metric space must be compact. We're going to use these three facts. Recall that in the statement of the theorem, we assume that gamma is a compact valued correspondence, which means that for any given value of theta, gamma of theta is a compact set. And we also assume that f is real valued and continuous. Now this implies from Weierstrass's theorem that there exists at least one element of gamma of theta for which the value of f is maximized. In other words, gamma star of theta is non-empty for every theta. Next, consider the image under f of the pair gamma star of theta, theta. This is just the value of the objective function when the parameter value is theta and the action is chosen from the set gamma star of theta. And this of course is just a singleton, it's just the maximized value of the objective function. And since f star of theta is finite, it must be closed. Now since f is continuous, the inverse image of every closed set must be closed, and gamma star of theta is the inverse image of f star of theta. Remember that theta here is being held fixed, so gamma star of theta is a closed set. Now gamma star of theta, which is the set of optimal actions at theta, is clearly a subset of gamma of theta, which is the set of feasible actions at theta. And so gamma star of theta is a closed subset of a compact set because gamma of theta is compact by hypothesis. And therefore, since every closed subset of a compact set is compact, gamma star of theta itself must be compact. So we've proved one of the three claims that this theorem makes, that the solution correspondence is compact valued. Next we're going to show that it's upper hemicontinuous at theta. To prove this, consider any sequence of parameters, which we denote theta n, such that the sequence converges to theta. Remember, we are trying to establish upper hemicontinuity of the solution correspondence at theta. Now we know that gamma star of theta is non-empty at every theta, so we can construct a sequence of actions, let's call it xn, such that xn is an optimal action whenever the parameter value is theta n. So corresponding to this sequence of parameters theta n, we have a sequence of optimal actions xn. Now obviously, since xn is an optimal action, it must also be a feasible action at theta n, so xn is an element of gamma of xn, which is the constraint correspondence. Now recall that we have assumed that gamma is compact valued and upper hemicontinuous at theta. Now since gamma is compact valued, we can use the sequential definition of upper hemicontinuity. Now recall this definition. It states that for any sequence in the domain, and this is our theta n sequence, and any sequence in the codomain, which we are calling xn, such that xn is an element of gamma of theta n, it must be the case that this xn sequence contains a subsequence, which we'll call xnk, such that the subsequence converges to a point x in the image of theta. And this follows directly from the sequential definition of upper hemicontinuity, which is equivalent to the neighborhood definition, provided that gamma is a compact valued correspondence. Now let theta nk denote the corresponding subsequence of parameters. So what we've done is, we've got a subsequence of the set of actions xn, and we extract from the sequence theta n of parameters a subsequence theta nk, such that xnk is an optimal action when the parameter happens to be theta nk. Now consider any point z in the image of theta under gamma. Remember, gamma is the constraint correspondence. It tells us which actions are feasible at theta. Now recall that by hypothesis, gamma is continuous at theta, so in particular, it's also lower hemicontinuous at theta. Now recall the sequential definition of lower hemicontinuity. What does this say? It says that for any point z in the image of theta under gamma, and for any sequence in the domain, let's say theta nk, there exists a sequence in the codomain, and we're going to call this znk, such that znk is in the image of theta nk under gamma for every term in the theta nk sequence, and the sequence znk converges to the point z. This must be true for every z in the image of theta under gamma, if gamma is lower hemicontinuous at theta. Now note that the objective function f, when evaluated at xnk theta nk, in other words, when the parameter value is theta nk and the action chosen is xnk, must be greater than or equal to the objective function evaluated at znk theta nk. And this must be true for all nk. Why is this? Because when the parameter value is theta nk, znk is a feasible action and xnk is an optimal action. So the objective function must take at least as high a value under the optimal action as it does under the feasible action. And now we can finish the proof by recalling that f is continuous by hypothesis, and since f is continuous, and since x is the limit of the xnk sequence, and z is the limit of the znk sequence, the limits must be also ordered in the same way. The objective function f evaluated at x theta must be greater than or equal to the objective function f evaluated at z theta. And this must be true for all z in the image of theta under gamma. Now this is not completely obvious. To prove this, just think about what would happen if this inequality were reversed. In other words, if there existed some z that was feasible at theta, such that f of x theta was strictly less than f of z theta. In this case, using the continuity of f, you should be able to show that our claim that at every point in the theta nk sequence, f of x nk theta nk is bigger than or equal to f of z nk theta nk couldn't possibly be true. In other words, you'd get a contradiction. So we conclude that the objective function f evaluated at x theta is greater than or equal to the objective function f evaluated at z theta for all values of z. And this of course means that the action x is optimal at theta. In other words, x belongs to gamma star of theta. Now think back to the sequential definition of upper hemicontinuity and think about what we've shown. We've shown that if you take a sequence in the domain, the theta nk sequence, and you take a corresponding sequence in the codomain, which is the xnk sequence, such that xnk is an element of gamma star of theta nk, then the limit of the xnk sequence, which we called x, is an element of gamma star of theta. And this is precisely what we mean by the upper hemicontinuity of gamma star at theta. And this completes the proof that gamma star is upper hemicontinuous at theta. It still remains to be shown that f star is a continuous function, but we'll do that in the next segment. And we'll also spend some time in the next segment discussing the implications of this result, which allows for the possibility that the solution correspondence gamma star is not lower hemicontinuous at theta. We'll see that this somewhat dry and technical result actually has an important economic implication. But we'll do that next time and end the segment here.